Hey guys, how we doing? Right, I think that's enough banter for one day. Let's get on with it, shall we? It's Jan12, and I'm going to be talking about maths today. FP2, Jan12, question 8, AQA. Right, yeah, get to that paper. This one's about roots and complex numbers. Quite a difficult topic, probably one of the most difficult out of FP2. I certainly never liked these questions. Right, 8a. Write down 5 roots of the equation z to the power 5 equals 1. And z has to be between, no, theta. They want it in the form e to the I theta, where theta is between minus pi and pi. Regular subscribers to this channel, to this series of videos that Andrew does maths, regular subscribers will know that there's a question like this recently where theta had to be between minus pi and pi, and I missed it the first time and I went above pi, so I know to watch out for this time. Cool, so z to the 5 is equal to 1. What does 1 look like as a complex number? If we write both sides as a complex number, it would probably be easier. Well, on the Argand diagram, 1 is there with no argument and just a modulus of 1. So complex number with no argument and a modulus of 1 is e to the I 0, or just the real number 1. But the reason why we write it like this is so we can generate 5 solutions. Because we know something to the power 5 is going to have 5 real or complex solutions. So this is the first one that we're going to make available to it. What else equals a number 1 though? Let's get an identical number that equals a number 1 so we can come up with another solution. How do we do that? We go all the way around the Argand diagram and back to 1. That's a full 360 degree rotation, or as we should be thinking about it now, that's going 2 pi around. So if we add 2 pi onto the argument, that's e to the 2 pi I, and we keep on going to get 5 numbers. E to the 4 pi I, e to the 6 pi I. No, I've done it again. Well, I'll write it out for now. E to the 6 pi I and e to the 8 pi I. So to find out what z is, we raise both sides to the power 5th, because a 5th multiplied by 5 would give us z. So we divide all the powers by 5. That number's just 1 anyway. We'll have e to the 2 pi I on 5, e to the 4 pi I on 5, and then what I was talking about is if we kept on going, this would be e to the 6 pi I on 5. 6 pi I on 5, that's gone over pi now, because that's 1.2 lots of pi. So instead, we're going to change this 6 pi I, we're going to go back round the other way. Remember when we go clockwise? Yeah, when we go clockwise, we take off 2 pi. So this solution isn't e to the 6 pi I, because that would be out of our range. This is e to the minus 2 pi I and e to the minus 4 pi I. And that gives us the last 2 correct solutions then in our range of e to the minus 2 pi I on 5 and e to the minus 4 pi I on 5. So you have to be careful with your range there. You have to make sure that if you're going out of your range, just go around the other way to generate more solutions that are inside your range. Okay. So we've got the 5 solutions of this now. Okay. Now the next question asked us to find 4 linear factors of z to the 4 plus z to the 3 plus z to the 2 plus z plus 1. But the big clue here is the word hence. This means that we're going to be using the roots, or we're going to be using something to do with part A here. Now we found 5 roots of the equation z to the 5 equals 1. This means that we've got 5 linear factors of z to the 5 minus 1. So z to the 5 minus 1 equals 0. We can split into 5 linear factors. Maybe we can use that to help us here. How can we rewrite this into z to the 5 minus 1, or doing something that includes z to the 5 minus 1? Because remember, if we can get this as z to the 5 minus 1, we know 5 factors of z to the 5 minus 1 using the roots that we've just found. So how can we make this into z to the 5 minus 1? Well, I can see how to get the z to the 5. I'm going to multiply this whole thing by z. So z to the 4 plus z to the 3 plus z to the 2 plus z plus 1. If I multiply this whole thing by z, I get my z to the 5. But annoyingly, I'm also going to get, if I do this multiplication, I'm also going to get a z to the power 4. Well, I don't want a z to the power 4, so how can I get rid of that? Well, if I multiply this z to the 4 by minus 1, that will cancel out with this z to the 4. And the pattern keeps on going like that. Z multiplied by z squared gives me z to the power 3, which I don't want, but it's okay, because minus 1 multiplied by z to the power 3 gives me minus z to the power 3, which cancels out. All of the in-between terms, z to the 4, z to the 3, z to the 2, z to the 1, they all cancel out, leaving us with minus 1 multiplied by 1 is minus 1. So this whole thing is equal to z to the 5 minus 1. And that's really good because we know the 5 linear factors of z to the 5 minus 1. One of them is z minus 1. And the other 4 must be 4 factors of this then. So that would be z minus e to the 2 pi I on 5, z minus e to the 4 pi I on 5, z minus e to the minus 2 pi I on 5, and z minus e to the minus 4 pi I on 5. So there's our 4 factors of this. Great. Cool. I've slightly forgotten how to do the next question. Hopefully it will come back to me. Oh yeah. Yeah. Yeah, okay. So we know that z to the 5 minus 1 is equal to 0. So this whole thing is equal to 0, and we could divide by both sides by z minus 1. So this whole thing is equal to 0. Just thinking, what's the right way to explain this? If you look at the answer, if you look at what you're going to get to, it's got cos 2 pi on 5 in there, which suggests to me, we've got e to 2 pi on 5, maybe we can make that into cos 2 pi on 5 plus sine 2 pi on 5. But the problem is we're going to have a sine 2 pi on 5, which we want to get rid of. And this comes back to the properties of the sine and cos graph that I spoke about in my last video of this. So just a quick reminder, cos is a reflection of itself about the y-axis. So that means cos x is equal to minus cos of minus x. And sine is similar. Sine is a reflection of itself, but upside down. So sine x is equal to minus sine minus x. I got the cos wrong. Cos x is equal to cos minus x. Cool, so we're going to use that to cancel out the signs and hopefully be left with what we want to be left with. So remember that z to the 4 plus z to the 3 plus z to the 2 plus z plus 1 is equal to this. So let's have a look at that, and I'm going to pair brackets in terms of their roots. So looking at those 4 linear factors then, we have z minus e to the 2 pi over 5 multiplied by z minus e to the minus 2 pi over 5 multiplied by z minus e to the 4 pi over 5 and z minus e to the minus 4 pi over 5. Cool. I'm just going to expand these two, and then you can expand the other two using the same pattern. So z multiplied by z is z squared, and then I have minus z times e to the minus 2 pi on 5 minus z times e to the 2 pi on 5, and e to the 2 pi on 5 times e to the minus 2 pi on 5. If we add those indices together, if we add the powers together, they cancel each other out, giving us e to the 0, which is 1. And the minus times by the minus makes it a plus 1. What can we do next? We can factorise minus z out here. So this is z squared minus z times e to the 2 pi on 5 plus e to the minus 2 pi on 5, and then plus 1 outside the bracket. Now this is really good, because I've got e to the power and e to the negative version of the power. So if I write that in its cos sine form, the signs are going to cancel out, because I've got a sign of a plus and a sign of a minus. And as we can see, those are opposites of each other, so those will cancel out. So that's what I'm going to do next, write it out in its cos theta plus I sine theta form. So minus z lots of cos to the 2 pi on 5 plus I sine to the 2 pi on 5 plus cos to the minus 2 pi on 5 plus I sine to the minus, not to, sine of minus 2 pi I on 5. So what will happen, oh, and then plus 1 as well. So what will happen is that this sine will cancel out with this sine, because they're just opposites of each other. And this cos will combine with this cos because they're identical. So that gives us z squared minus z lots of 2 cos to 2 pi I on 5 plus the 1. Now if you do that with this pair as well, I'll write down what you get. And remember, this whole thing was equal to z to the 4 plus z to the 3 plus z to the 2 plus z plus 1. So if I write that out now, so we've got z to the 4 plus z to the 3 plus z squared plus z plus 1 is equal to this multiplied by what you get when you expand these two brackets. So z squared minus z Oh, I've gone wrong somewhere. It doesn't quite work out. What have I done? I'm going to have a quick look at the marks. I'm not quite sure. Yeah, there's a factor of Z I'm missing somewhere. I'm not sure where. I'll write down what this is anyway. So Z squared minus Z times cos. That'll be 2 cos. 2 cos 2 pi on 5. Shouldn't be annoying that. Plus 1 multiplied by Z squared minus 2Z cos 4 pi on 5 plus 1. So if we divide the left-hand side by Z squared, we get what the answer is, but we only need to divide the right-hand side by Z. So I'm not sure what's gone on there. I'm just going to have to say, let me know if you find out. Yeah, sorry about that. Please do let me know if you can do this question, because I can't. I might have another crack at it tonight, but for now I can't do it. So let me know if you can. I mean, I probably would have got 3 marks out of 4. That's annoying. Never mind. Let's assume that answer. I mean, let's do what we would do if we were actually doing the exam now. I can't get that question. It's 3 marks out of 4. I'm just going to write down the answer now and use the answer in the next question. So I'm going to write down the answer, say that I got it right, and just forget about it and move on to the next question, because that's what we would have to do if we were in the exam. That's the best thing to do if we were in the exam. Forget about it, move on, let's do the next question. Right, so I'm going to write down that answer. Okay, so writing down the answer, z squared plus z plus 1 plus z minus 1 plus z minus 2 is equal to z minus 2 cos to the 2 pi on 5 plus 1, z minus 2 cos 4 pi on 5, sorry, it wasn't plus 1, plus z to the minus 1, plus z to the minus 1. And we're going to substitute on both sides z plus z to the minus 1 is equal to w. Okay, so we've got z plus z to the minus 1 on the left-hand side. We can make that into w. How does z squared plus z to the minus 2 work with this? It looks like we can get z squared by squaring this. So let's square both sides and see what happens. So z plus z to the minus 1 squared is equal to w squared. Probably omega. Who cares? Oh no, it's w, doesn't matter. Right, z squared is z squared. Z multiplied by z to the minus 1, you add those powers and you get z to the 0, which is 1, and 2 lots of that would give us plus 2. And z to the minus 1 squared is z to the minus 2 equals w squared. So z to the 2 plus z to the minus 2 is equal to w squared minus 2. And so I'm going to substitute for both sides now. So z squared plus z to the minus 2 is w squared minus 2. Z plus z to the minus 1 is w. And I've still got that plus 1 there. So plus 1. And minus 2 plus 1 will give me minus 1. I'll do it next. And then in both of these brackets, I've got a w. So z plus z to the minus 1 is w. So first bracket, I've got w minus 2 cos to 2 pi on 5. And the next bracket, I've got w minus 2 cos to the 4 pi on, not 2, of 4 pi on 5. Cool. And so the left-hand side is w squared plus w minus 1. So we've got w squared plus w minus 1, which is a quadratic, is equal to w minus something times w minus something. Well, what does this look like? This looks like a quadratic, and it's 2 roots. So let's find the 2 roots of this equation in its complex form, and those 2 roots would equal 2 cos 2 pi on 5 minus 2 cos 4 pi on 5. So how can we find the roots of this equation here? Let's use the quadratic formula. So w is equal to minus b minus 1 plus or minus the square root of b squared, 1 squared is 1, minus 4ac, 4 times minus 1 times 1 is plus 4, all over 2a, so all over 2. So w is root 5 plus or minus 1 over 2. We've got the root 5, which is in our answer, so that's looking good. So therefore, the 2 roots of this equation here are root 5 plus 1 over 2 and root 5 minus 1 over 2. So if I were to write that out in linear factors, that's w minus root 5 plus 1 over 2, w minus root 5 minus 1 . I'm sure I've got that wrong. Not doing very well today. That must be plus or minus root 5 minus 1. So there's, probably put that in brackets, we'll have it a little bit more. W minus root 5 minus 1 over 2, and W minus root 5 minus 1 over 2. So either 2 cos 2 pi on 5 is equal to root 5 minus 1 over 2, or minus root 5 minus 1 over 2. Well, if you know your cos graph, 2 pi on 5 is in the first quadrant. The first quadrant between 0 and pi on 2 of the cos graph is positive. So we know that cos 2 pi on 5 is positive. So we know that this must be equal to root 5 minus 1 over 2, because that's a positive one. So 2 cos 2 pi on 5 is equal to root 5 minus 1 over 2. If we divide both sides by 2, cos 2 pi on 5, that's root 5 minus 1 over 4. And that's the answer. Great. So 6 marks there. Didn't get 4 marks in the previous question. Probably would have got 3 or 2. But that's, that's the way the world works, isn't it? Yeah. Please let me know if you can get part C. Please let me know if you think it's a mistake in the question. Probably not a mistake in the question. That's probably wishful thinking on my part there. Cool. Okay, that was a tricky one. Good luck, guys, with everything.